Hello everyone, and welcome to the session Building and Deploying PyTorch Models with Azure Machine Learning. My name is Henk Boelman, and I work as a Senior Cloud Advocate focusing on Azure Machine Learning. AI is changing the world, and at its core are machine learning models. As machine learning becomes mainstream, an increasing amount of organizations are seeking to adopt an enterprise-grade MLOps platform that will assist them in delivering responsible machine learning solutions more quickly. This is where Azure Machine Learning comes into play. Today I'm thrilled to present some exciting features of Azure Machine Learning that will help you implement MLOps into your organization and streamline your model development and deployment. Before we dive into Azure Machine Learning, let's examine how Microsoft develops AI technologies. At Microsoft we have 8 research centers around the world, hosting thousands of researchers who specialize in fields such as computer vision, human language, and autonomous systems. We have amassed an impressive portfolio of 22,000 patents and over 3,500 research papers specifically related to AI. Building on this foundation is our collection of AI services, which are not only accessible to all of you, but are also utilized by other Microsoft product teams to revolutionize their business. We make available externally exactly what we use internally. Let's take a look at our AI service portfolio. Our AI is embedded and tested in numerous Microsoft applications. For instance, if you use Office 365, you may have encountered PowerPoint's designer capabilities when inserting a picture onto a slide, as it offers redesigned slide ideas. Or in Outlook, you might have used suggested quick replies. These incredible features are trained on Azure Machine Learning. Millions of Office users daily enhance and validate the quality and scale of Azure Machine Learning, which all of you can benefit from. With the Azure AI stack, you have the flexibility to start as high as possible and go as low as needed. At the top, with Azure Applied AI Services, you can utilize specific applications such as bot service and form recognizer. Below that are cognitive services, which consist of domain-specific pre-trained models. Cognitive services are built upon the foundation of Azure Machine Learning. As a user of cognitive services, you don't need to know this. However, if you desire access to that foundational layer, you can obtain it by using Azure Machine Learning directly. Azure Machine Learning is a comprehensive managed machine learning platform for creating, training, deploying, and operating machine learning models responsibly and securely at scale. Now, for those of you who haven't yet used Azure Machine Learning, let me provide an overview before transitioning to some exciting demos. It all begins with data, and Azure ML supports various data sources for data preparation, including those shown on the left side of the slides. Whether you're working with structured or unstructured data, Azure ML has you covered for building models based on your data. If we skip the intermediate phase, it concludes with machine learning models in production. Models that are utilized by either your own custom application or by another Microsoft project, as seen at the right of the slide. These models can be invoked in real time, such as calling a REST endpoint, or in a more batch processing style, like in the context of a stored procedure. One key takeaway is that Azure ML is not an isolated entity. It is well integrated with all relevant Microsoft products. Last year, we introduced the Microsoft Intelligent Data Platform. Azure ML is a crucial service that connects these two layers displayed on the slide, transforming data into actionable insight. Let's take a closer look at the Azure ML box to see what's inside. The way you typically interact with Azure ML is through the Azure ML Studio web user interface. You have options of building and training your model using automated ML, which is a no-code approach. The designer and the built-in drag-and-drop components, which is a partial code approach, or a full code approach with scripts and notebooks. When you choose the scripts and notebook approach, you can do that in your favorite editor if you have one, like VS Code. Or you can do it right into the Azure ML Studio UI. and you can bring whatever library and framework you wish, such as TensorFlow, PyTorch, or anything else. As you build your model, Azure ML keeps track of everything, so that you know who is doing what and what is getting used and how. Azure ML facilitates a reproducible process all the way to deployment and monitoring. You can run all that in the cloud on Azure ML Compute instance or via Azure Kubernetes service. And also on-premise by bringing your own Arc-enabled Kubernetes clusters. You can even do hybrid between Azure, on-prem and other clouds. Regardless of where your computer is, Azure ML can help you implement a responsible MLOps process for your entire ML lifecycle. When discussing the ML lifecycle, you have likely encountered the standard representation of the machine learning lifecycle, which appears as a linear progression illustrated on the slide. Theoretically, and if viewed from a distance, the reality is somewhat similar to this linear approach. You prepare your data, build a model, train it, deploy it, and monitor it. Azure ML can assist you in each and every one of these phases. Today, I'd like to share with you a more realistic view of the enterprise ML lifecycle, which is a more intuitive and represents a more agile approach of going back and forth between different phases as if it was circulating in multiple loops. This interactive loop structure is still underpinned by responsible AI and MLOps, but focuses on a non-linear and iterative nature required in the practice of data science at scale. First, we have the prototyping loop, which is centered around experimentation. In this loop, you have typically a single data scientist working locally, which can mean on their own local machine or on the workstation in the cloud using an exploratory, interactive approach. They work with a subset of the data, getting to understand the shape of the data in the context of the business problem. When they are successful, the result is a minimal viable model, and the lifecycle advances to the next loop for training. In the training loop, it is all about scaling. Scaling to the full large dataset and scaling to larger and additional compute targets. We also want to ensure that the experiments are reproducible and easily repeatable via automation, breaking the notebook files into modules or components. When the team is happy with the results of training and validation, the output of the training is a candidate model that is ready to be prepared for production. Then we progress to the third loop, operationalizing. It's in this loop that we deploy to production the model for inferencing. It includes packaging the model, online validation of performance and running A/B tests to ensure that we're serving the best model for the job. Essential to this loop is monitoring. This is how we know if the model begins to drift, whether due to the data or due to the concept. We may need to move back to the training loop to retrain the model with new data, or even revert the project back to prototyping if the algorithm itself needs to be revisited. An overall takeaway from our observations is that the enterprise machine learning lifecycle is an inherently messy practice. It begins with creativity at the prototyping loop, and as that lifecycle progresses, it must become increasingly rigid to conform with enterprise requirements. Now that we have a high-level understanding of what Azure ML has to offer and how we view the end-to-end enterprise machine learning lifecycle in the real world, let's see Azure ML in action. In this first demo, I want to show you how you can use Azure Machine Learning to quickly prototype and validate a model using Azure ML Studio. In this demo, I want to demonstrate how Azure Machine Learning can be used to prototype and shape your models effectively. We will be creating a PyTorch classification model using transfer learning. Our training data consists of images of 30 distinct Lego figures, and the goal of the model is to accurately classify these figures. Within the Azure Machine Learning Studio, you can utilize notebooks to develop your model. Let's begin by creating a new notebook. We can add code to the notebook, but in order to execute it, we need access to compute resources. Navigate to the Compute tab to create several different compute options. For this demo, we will create a compute instance to run our notebook. An Azure Machine Learning Compute instance is a managed cloud-based workstation designed for data scientists. Each compute instance has a single owner, but files can be shared among multiple instances. We click New and provide a name. We can choose between a CPU or GPU virtual machine, select the machine size, and under Advanced we can enable options such as SSH access, or we can deploy it in a virtual network, and finally automatically shut down after 60 minutes of inactivity or based on a schedule. These options really help in reducing costs. Click Create and in a few minutes our compute resource will be ready. With the compute resource available, we can return to the notebook. Select the newly created compute resource and the desired environment. You can use a pre-built environment or create a custom one. For this project, we can select a Python 3.8 with PyTorch support. Let's add some code to the notebook. Begin by importing the required dependencies and adding the training script. This script is a slightly modified version of the transfer learning example found on the PyTorch website. For prototyping purposes, we will use a subset of the data which includes 4 classes: Yoda, Itchy, Stargirl and Jar Jar. The data is already stored on my disk. After completing the training, the model is saved on the disk. Now it is time to evaluate the model's performance by running some tests. For testing, we select 4 images that the model has never seen before. We run these images through the model and the result we will display alongside the images. And as you can see here in the result, our model is able to classify our Lego characters correctly. You saw in this demo one of the many approaches you can use with Azure ML to quickly prototype and get to a working ML model. Regardless of whether you want to take a code-first approach with notebooks or Python scripts like in the demo, or whether you start with the Azure ML drag and drop designer, or whether you start with automated machine learning. You will want to scale the training and making it a repeatable and automatable process. One of the most powerful ways is to do this using Azure Machine Learning pipelines. In this next demo, I will show you how you can use Azure ML pipelines to train your PyTorch models at scale and in a repeatable way. In this demonstration, I will show you how to train your model using an Azure Machine Learning pipeline and its components. An Azure Machine Learning pipeline is an independent executable workflow for a complete machine learning task. The essence of a machine learning pipeline is to divide a complete machine learning task into a multi-step workflow. Each step is a manageable component that can be developed, optimized, configured, and automated individually. The Azure Machine Learning Pipeline Service automatically orchestrates all dependencies between pipeline steps. An Azure Machine Learning component is a self-contained piece of code that performs one step in a machine learning pipeline. A component is similar to a function having a name, inputs, outputs, and a body. The pipeline we are going to construct consists of 2 steps. To create our pipeline and components, we will be using a GitHub Codespace. GitHub Codespace allows developers to create cloud-based development environments from repositories, enabling work on any device and location. To create our pipeline, I've chosen to use the Azure Machine Learning command line interface, also known as the Azure ML CLI. The CLI offers commands to create and maintain Azure Machine Learning assets and workflows. These assets or workflows are defined using a YAML file, which specifies the configuration of the asset or workflow, such and its purpose, where it should run, and other details. Everything that can be done using the CLI can also be accomplished using the Python SDK. To train our models, we require an environment in which the training can take place. Azure Machine Learning environments encapsulate the settings where your machine learning training occurs. These environments specify the Python packages, environment variables, as well as runtimes like Python, Spark or Docker. As managed and versioned entities within your machine learning workspace, these environments enable reproducible, auditable, and portable machine learning workflows across various compute targets. Azure ML offers curated environments, which are pre-built environments provided by Azure Machine Learning and available in your workspace by default. Designed for immediate use, curated environments contain a collection of Python packages and settings to help you get started with various machine learning frameworks. We are training a PyTorch classification model, and we can accelerate our training process by using the Azure container for PyTorch. It is a lightweight standalone environment that includes the necessary components to effectively run optimized training for large models on Azure Machine Learning. In this demo, we create an environment named ODSC ACPT, based on the Azure container for PyTorch with PyTorch 1.13, Python 3.8 and CUDA 11.7, optimized for the GPU. We run the CLI command azml environment, and our environment specification is created in our Azure Machine Learning workspace. We can locate the environment by going to the studio and clicking on Environments. Now that we have an environment in which our scripts can run, we can proceed with creating the components. The concept for components is the same as for environments. Place the specification of a component in a YAML file and use the azml command to execute it. Let's take a look at the specification file for the training component. We start by giving the component a name and a version number. Then we define the input parameters, which are sent to the training script. In our case, the input parameters include the location of our training images and some model parameters. Our script also generates output, specifically the trained model. Under Outputs, we can specify where the output files will be saved. The code section points to the directory where the training script is located. I have placed the script in the source folder. Everything in that folder is copied to the component, so ensure all necessary files for your component are in that folder. In my case, it is the train.py file, so let's take a look at that file. I have used the transfer learning example from the PyTorch website and added a few things. I've included a reference to MLflow, so that in my training loop I can log my accuracy and loss. Just by adding these 3 lines of code, the result will be visible in Azure Machine Learning Studio as an attractive graph, and I can use it later to compare different training runs. Also, at the beginning of the script, I parsed the input parameters. Next, I point to the environment we created a few minutes ago. And finally, we specify the command the component should run. Here you can see that the input specified above can be parsed into the command by using the input variable name. Now, let's run the component to create the train component and the second component that registers our model. These components are now visible in Azure Machine Learning Studio. Now that we have our components, we can incorporate them into a pipeline. For this, we also create a specification file in YAML format. We begin by specifying the experiment name. An Azure ML experiment represents a single run or multiple runs of a machine learning process. Experiments help track code, data, parameters, metrics and outputs, enabling better organization, reproducibility, and collaboration in machine learning workflows. Under Settings, we point to the default compute cluster and data store. To speed things up, we are using a dedicated compute cluster with Tesla V100 GPUs named Ultra Magnus. However, you can also choose to use the serverless option here, which will save you from having your own dedicated cluster and significantly speed things up. Under Inputs, we define the location of our training data. Here we point to a dataset in Azure ML called Lego Characters v2 with version number 2. This dataset is located under the Data tab in Azure ML Studio and consists of 30 classes with Lego characters. Under Jobs, we point to the components we have created in the previous steps. We assign them a name, point to the component and version to use, and specify the input and output. As shown in this example, we use the output from the training step as input for the register step. Our pipeline configuration is now complete. Let's run it and see what happens. We can monitor our pipeline by going to the Azure ML Studio and click on Pipelines and select the pipeline that is running. Here we see the different components of the pipeline and the status. Great, our model is finished. Let's take a look at the log files that MLflow generated for us during the model training. In the final pipeline step, we saved our model, which can be found under the Models section. Let's quickly deploy this model and see if it works. There are multiple ways to deploy your model. You can choose a managed endpoint, which is an excellent option for production workloads. Since we just want to test if our endpoint is working, we can choose to deploy it as a web service. We assign a name to the deployment. Choose an Azure Container instance by selecting the computer type. Authentication can be enabled if desired. Select a scoring script, which is responsible for taking input images, converting them into the appropriate tensor, processing them through the model, and returning the output. Choose a conda dependency file that contains the necessary packages to run your script. In the advanced settings, we can modify the CPU and memory allocations for our model, as well add SSL support and enable application insights. Click Deploy, and within a few minutes an endpoint with our model will be up and running. To view the deployment, navigate to the Endpoint section. Here we can see how to consume our model and perform a quick test. The quick test works. Let's go back to our code space. I've created a script that will send a lot of images to our endpoint and displays the result of the model below every image. Great! It looks like that our model running in our endpoint predicted everything right. In this demo you saw components and pipelines in action. They are the building blocks for operationalizing models, and they are foundational to an MLOps platform. You also saw in this demo the Azure container for PyTorch. It is a great example of our partnership we have with Meta. In the next demo, I'll show you how you can move your model from the training phase and get it into production. In this demo, you will learn how to scale MLOps across development, testing and production environments. For example, you may need to train a model in your development workspace, but deploy it to another endpoint in a production workspace. In this situation, you must be able to trace back the training job, such as analyzing the metrics, logs, code, environment, and the data used to train the model if accuracy or performance issues arise in the production deployment. Registries, similar to a Git repository, separate ML assets from workspaces and store them in a central location, making them accessible to all workspaces within your organization. To promote models across environments, development, test, production, begin by iteratively developing a model in the development environment. Once you have a suitable candidate model, publish it to the registry. From there, you can deploy the model to endpoints in different workspaces. Let's create a new repository called ODSC Registry. We deploy it in My Subscription, select a resource group. In the next step, we select the primary region, and if we like, we can specify additional regions. Click Create and we will have our registry in a few minutes. Let's go back to our workspace Cybertron and the classification model we have trained earlier. On the detail page from the model, we can click Share Model. Select the registry and click Add. Now our model is available in the registry where other people can access it and deploy it. But it is still linked to the pipeline that was used to create the model. In my production workspace, I want to deploy this model into an online endpoint. Online endpoints are endpoints that are used for online real-time inferencing. Online endpoints can have multiple deployments of different models, and every deployment can use a different VM underneath. The endpoint can route a percentage of traffic to one deployment and another percentage to the other. To start the deployment of a model, we find the model in the shared assets and click Deploy. Here we select a real-time endpoint, My Subscription, and our production workspace. We give the endpoint a name, select Manage Compute, and we're using basic key-based authentication. We use the model we have selected, and now it is time to customize our first deployment. We call the deployment version 1 and enable application insights to get insights back about the performance of our model. In the next step, we select our scoring script and select the Azure container for PyTorch. We select a GPU-enabled NC6 virtual machine and route 100% of the traffic to this endpoint. We click Create, and within 10 minutes our online endpoint is up and running. Of course, everything I showed you here can be done using the Azure CLI or the Python SDK. The first deployment is finished. Now let's add another deployment. We use the same model, but this time we choose for a cheaper virtual machine with only a CPU. We route the traffic half-half to both deployments. When version 2 is deployed, we can go to the Test tab in the endpoint to test both endpoints to see if they're working as we expect. Great, they're working. Now let's start sending some more traffic to the endpoint. In the Monitoring tab we can compare both deployments. From here we can make an informed decision about which deployment we want to keep. For more advanced metrics, we can go to the Application Insights. Finally, let's run our testing script to visualize the output of our deployed model. Under Consume we can find the API endpoint and the API key. And yes, as you can see, our endpoint is predicting all the images right. That wraps up the demos for this session. Let's review some of the highlights. You saw the demo Azure ML registries. Using registries will help collaboration across your team and across your projects. Registries will accelerate your MLOps journey. Registries provide a central repository for assets such as models, components, and environments that can be referenced from everywhere, all while keeping governance, lineage, and tracking across all the Azure ML workspaces. Also, you saw the Azure container for PyTorch, with pre-installed and pre-configured packages that ensure your workloads will go as fast as possible. You saw how we used components and pipelines in actions. They are the building blocks for operationalizing models, and they're foundational to an MLOps platform. And finally, we showed you how you can use managed pipelines to run your model in production and monitor them. I also want to mention the Responsible AI dashboard, which includes multiple tools to help identify bias and debug the model. These tools are helpful, if not essential, in highly regulated industries and for scenarios with sensitive data. Even if you're not in a regulated industry yet, and even if you're not working with sensitive data, you should check out these tools in the Responsible AI dashboard, which will help you create high-quality models in general. In the demos, you saw a lot of the Azure ML Studio UI. With Azure ML, our goal is that everything you can do in the UI, you can also do it with the SDK and the CLI. All the code shown in the demos is available on ak.ms/henk/odsc. Thank you for joining us in this session. You now know by using Azure ML, you can improve your time to value with integrated tools. You can operationalize at scale with MLOps to deliver responsible solutions. And you can rest assured you're doing that development on a secure, hybrid, and compliant platform.